All right, so our next topic here is efficiency, which is definitely key, is the efficiency of any machine, person, device can be worked out using the following equation. All right, so we have efficiency is equal to, you take the useful amount of energy that you output, and you divide it by the total energy that actually went in, and then you got to multiply it by 100% afterwards, because when you divide these two, you're going to get a decimal of some sort, and then to convert it to a percentage, we multiply by 100%. All right, so to start off, it says a large wind turbine is able to transform 1,500,000 joules of mechanical energy. Mechanical just means it's moving, into 900,000 joules of electrical energy every second. How much energy does this turbine waste each second? All right, so here's kind of a way I like to do a diagram is we have all this energy in. That's our total energy. So ET, total energy comes in. We have 1,500,000 joules of energy. Now what happens is some of it gets directed outwards here. Not a very good artist, but I'm going to do my best here. So put a little arrow. This is our energy output, which is the useful energy, the output. I guess you could call this the input. All right, now this total here is 900,000. That's the output. That's our useful energy that's going on there. All right, and now what's going to happen is that we have this section of it that's just wasted energy. All right, so again, in our formula here, I'm going to call that E out, the output, and this is E in, the input. And what we have left here is, well, our, E waste. The wasted energy. All right, and we can find that by just finding the difference in the amounts. And so the difference in converting difference to math means subtract. What's the difference here? So if 1,500,000 was put in, 900,000 is useful. Well, the rest, the difference, is our wasted energy. And so that wasted energy in this case is, let's see, I take 1 million. Divided by 900, or subtract by 900,000, I end up with 600,000 joules of wasted energy. All right, so that's our wasted energy right there in red. Now, it says calculate the efficiency of this turbine. So again, the only values we need are going to be in purple. All right, the 1,500,000, that's our E in, that's the number that goes on the bottom. And our E out is the number that's going to go on top. All right, so when I'm calculating the efficiency, let's see here, we'll go with, so EFF, I'll call for efficiency, is equal to the output, E output, divided by the E input, the energy put in. And let's see, so in this case, the output, as I have up there in the diagram, was 900,000 joules of energy divided by the amount that's in, which is our 1,500,000. And then, of course, I can't forget the times 100%, because when you take these two numbers, 900,000 divided by 1,500,000, you're going to get a decimal. And so then when I do the calculations here, I take 900,000. I divide it by 1,500,000 and then times it by 100%. And the efficiency of this turbine is 60%. There we go. And so where did the wasted energy go? Usually it's heat or sound when it comes to a wind turbine. I don't know what the actual efficiency is. I just made this up. All right. Let's see. Let's try another one of those. Try something a little different here. A 100-watt light bulb, oh, so we're getting into power here, emits 25 joules of light energy per second. Calculate the efficiency of the light bulb. Okay, this is a little bit tougher here. So one thing we know is that the power of this light bulb is 100 watts. Now we looked at power, and power is the amount of energy per second that it uses. And so in this case, the power is telling us that it's using 100 joules per second. That's the amount of electrical energy it's dragging out. So that is going to equal our energy in. All right, now it emits 25 joules of light. That's it. So that is our output, E out, because that's what a light bulb does, right? It produces light, 25 joules of light. And this is, again, per second, and that's why we can use this 100 here as our E in. Now, again, calculating the efficiency, we have our EF. I'm going to call it EFF, efficiency. All right, we have our energy output, which goes on our top. I'm going to draw that in there. Let's do that in there. E output divided by the E in, how much electrical energy this light bulb uses. And I'll tell you, this is not going to be the right, well, we'll get to that. Output, so 25 joules. So a 25 on top. This light bulb is a 100-watt light bulb, and so it equals 100 joules per second. So we're talking about per second here. So the input is 100 joules of electrical energy. And again, I can't forget times 100%. All right, so my efficiency is that I'm going to take, let's see, 25 divided by 100. What do I get? 0.25 times 100%. I get 25% is the efficiency of a light bulb, of this particular light bulb. To be honest with you, a light bulb, now I'm not sure about the new ones, the energy efficient ones, but the older ones, the efficiency was probably 5%, believe it or not. So only 5% of the electricity that going into a light bulb went into actually producing light. The other 5% or 95% was generally used for heat. That's why light bulbs are so hot. But yeah, for the most part, light bulbs are very inefficient objects, but they've been around for hundreds of years. All right, let's try another one here. Here we go. An energy efficient 14-watt light bulb emits 5 joules of light energy per second. Calculate the energy efficiency of the light bulb. So again, this is one of those energy efficient ones, and it's only 14 watts. So again, that's our power rating of 14 watts, which again means we're talking in 14 joules per second, and that's what we have. So again, we're all talking about the seconds here. So that's going to be our E in. That's how much electrical energy it uses, and we're going to get into electricity later on this month. All right, now our E output is that it outputs 5 joules. Because if you have ever had an energy efficient light bulb, not always are they the brightest. And we are again looking for our efficiency. There, I spelled it right. All right, so again, I'm going to plug in. It's a different light bulb here, but same idea. We have our efficiency is equal to our output, our energy output, and our E in on the bottom. And again, times by the 100%. All right, so our efficiency here this time out is this time, again, output was 5 joules. It took up 14 joules. And again, I'm going to have to multiply by that 100%. All right, now 5 divided by 14, get quite a decimal there. But then I times it by 100%. And this light bulb is 35, 2 decimal places always, 0.71%. And there we go. So it's slightly more efficient. Now, again, I just made these examples up. I think that actually an energy efficient light bulb is probably around that 35 or 25% rate in real life, where the older ones are like I said, like 5%. Again, I don't know the exact numbers. And every light bulb's different, LEDs and all that kind of stuff. There's so many light bulbs now. When I was a kid, there's just like 2 light bulbs. That's it. You got a 60 or 3 light bulbs, 40 watt, 60 and 100. That's it. Now they got everything, especially when at Home Depot, there's like a whole row of light bulbs. All right. Let's see here. Number 4. Okay. That's all we're doing. All right. So a certain motor uses 1,300 joules of energy to raise a 30 kilogram mass to a height of 2.4 meters above where it started. How much potential energy does the mass gain during the lift? All right, so again, this is kind of back from our old formula of looking at gravitational potential energy. All right, so that's what this thing is doing, because it's increasing the gravitational potential energy because it's lifting it. All right, so again, our gravitational potential energy formula is mass times that G times ZH. All right, now this is a 30 kilogram mass. All right, our G value, well, we're still on Earth here, 9.8. And we raise it up 2.4 meters. All right, now I'm going to multiply that. And let's see here, I multiply the 3 numbers here. And I get to 705, going to 2 decimal places, 0.6 joules of energy. Well, that's how much gravitational potential energy this thing increases by. Now we get to B. Calculate the efficiency of the motor. Now this EG that we just had, believe it or not, is the result. And so that gravitational potential energy that is 705.6 joules is actually our output. That's the result of this motor. Now the motor, it says, uses up 1,300 joules of energy. And we are looking for its efficiency. Now here's something that I'll bring up, is that when you compare your energy output and your input, maybe you get confused on which one's which, right? That's a common thing that happens. Which one's which? Well, check out my formula here, because I'll show you something. E efficiency is equal to E out, the output, what actually resulted, divided by the input, times 100%. All right, now, when I plug these numbers in, output, again, the output resulted in this thing gaining gravitational potential energy, so 705.6 joules of energy, divided by 1,300. Now, again, how do you tell the energy output divided by the energy input? Which one's which? I'll tell you what, the energy input will always be the bigger number, because what you can't have is more than 100%. I know you might have some coaches out there or people saying give it 110%. You can't. You just can't do it. It's a nice figure of speech, but it doesn't happen, especially when we're dealing with machines. It just doesn't happen. You can't go more than 100%. So if you get a number that's over 100%, you know you got your numbers flip-flopped. All right, so now when I multiply or divide these two numbers and then times by 100%, what am I getting here? Again, going to 2 decimal places, the efficiency of this motor is 54.28%. So where did the other wasted energy go? Probably heat with motor, always heat, vibrations, movement, that movement of the motor, just slight vibrations, heat, sound, motors all make sound. So there's a lot of wasted energy there. But again, the efficiency of this motor is 54.28%. All right, so that, see here, whoops. And there we go.